Quantum Foam.
Episode 37, Analytic Geometry.
Quantum foam.
Physics. Physics is at the foundation of all the mathematical principles that guide the heavens. You have to understand physics.
More than likely that's not going to happen, but
Forces which govern the universe. Physics.
Alright, here we go. I'm able to produce pretty good audio quality inside of this vehicle, and now I am able to use my phone to record it at 16-bit 48 kilohertz .wave.
You are only some of the time recording at 48 kilohertz.
I wanted to give a quick overview of the topics that I may be going over the rest of the decimal. Quantum foam. So we had college physics, expert systems, audio engineering, the character of quantum law, miscellaneous topics, computational intelligence, and that's episodes 31 through 36, respectively. Quantum foam. The proposed topics to go into next are analytic geometry, times arrow, torsion fields, and Kepler's orbital mechanics.
You have 2 entire pages with lists of episodes that you need to cover. Remember, some of these subjects have prerequisites. They have to be done in order.
The topic I have to get into next is analytic geometry. Essentially, it's calculus. Just calculus. I don't even know what calculus is. Quantum logic tertiary math. Okay, that's probably not analytic geometry. The zeroth wave quantum compute engine.
Forces which govern the universe.
Yes.
The mathematical principles that guide the heavens.
Yes. We will have to go into these topics separately. The standard model, time and infinity. We have other things to think about here. The theory of everything. Spin math, dude. Linear calculus is essentially spin math because it can give you the most accurate representation of all arc angles down to a high degree of accuracy of a spinning circle to better than
202
billion digits of pi as far as how round.
That number keeps going up.
At that point, it decoheres and becomes inaccurate. So essentially, it is a spin math because one of the consequences of there being 2 dimensions as opposed to 1 is that there is a orthogonal force to the normal force.
This sort of thing takes practice in order to visualize.
So you have a direction of your vector that you're going. You're going north, you're traveling, you're walking, you're driving in a car. Your normal's obviously up to your zenith, directly up to the top of your head, an invisible axis that goes directly through your body, through your torso, and in through the top of your head towards directly upward, which is your zenith. So that's the normal force, and the orthogonal force vector is your forward motion. Your mass, 100 kilograms, F equals ma, so the force equals 100 kilograms times your acceleration, which is approximately 1 meter per second. So 1 meter per second, 100 kilograms is 100 newtons of force times about negative 9.8 meters per second squared, or in some places negative 9.81 meters per second squared. At sea level, approximately 14 pounds per square inch barometric pressure. It doesn't matter if it's day or night on this one.
That's very good. We need to do more on-set exercises to help everyone else learn the physics.
That's what linear calculus is. That's what linear calculus is. But essentially, linear calculus is math formulated to calculate anything pregeneratively. We're trying to be accurate, so we need to continue this forward.
At first I had an issue with adding a linear in front of calculus, but I have since come around. There is much more math that has been added since my day back when I published my book on calculus in 1687.
Linear calculus is a pregenerative software stack to allow you to calculate things and use MapleSoft and Desmo's scientific calculator and other Texas Instrument programs that do calculations. we're going over analytic geometry. That's not necessarily the calculus, but they group them together. Analytic geometry and calculus 1, 2, and 3, and then differential equations, and then mechanics, and then quantum mechanics, and then application-specific physics and mathematics. Essentially above that is conjectures, theories, algorithms, data structures, things like that. It gets into higher order mathematics.
Since we are going to be getting into some physics on set, I was thinking that we can get into some math as well. In a couple decimals we should be solving problems and going through techniques regularly.
But as of 2015, the largest prime number is calculated out to 2 to the 57 millionth power. So 2 to the 57 millionth power is essentially the largest prime number, and that's what we can build our binary number systems based on. That's what we can use for our binary operating system kernels. Physics and math must both agree. This is when we get into the separation of linear computers and quantum computers. We're going to need these different types of calculators, if you will, to work with prime numbers that are larger than 2 to the 57 million.
Oh, it's more.
Or whatever it is now. It's probably a couple million more or something. It takes a long time to build these numbers.
They have a lot better hardware today, so it is only a matter of time. We are only doing certain specific calculations here.
We're not going to be measuring paths or be doing any other type of teleportation ideas. I'm just reviewing some of the old stuff. How am I going to put this into analytic geometry? The idea of analytic geometry is actually just that you can analyze your math and prove when you claim something is equal to something. The Fundamental Theorem of Calculus, you can grab the scope of all the numbers in the number system, all the real numbers, 1, 2, 3, 4, 5, 1.1, 1.2, 2, 2.1, all the way up to 5, depending on how far your domain is.
They have recently found a Mersenne prime number 41 million decimal digits long. This information will likely get outdated fairly quickly.
Thanks, Doctor.
I'm more interested in the moving paths associated with these light cones.
Yes, I'll tell them about the light cones, I swear, I will.
We have been working on these for quite some time. Make sure to figure calculating a balanced design.
Yes, they will be a balanced design.
Just making sure.
Okay.
We could use ideas from that paper from Anderson and his associate.
Yes, we could utilize factorial association schemes.
I was looking over that the other day.
Yep, it's essentially that paper. He may actually be orthogonal, if you're correct. I would call that an orthogonal vector for sure. Yes, this was done 4.5 years ago. We're trying to find the B-line math here. In reality, we need analytic geometry so we can solve our calc equations in high school and college, and potentially when we're on a space shuttle that's off course a little bit.
That would be an intense experience.
The ideas of the calculus, a calculus. A calculus is a way to calculate things. It's the method by which you calculate things. It can utilize analytic geometry.
There are a great many different types of mathematical disciplines. For this subject, we are focusing on interpreting geometric figures streamlined into a standard notation which takes care of infinities and zeros.
But there are so many other types of math. Real number math, irrational math, imaginary math, quadrature math, basically 1 to 2 math, 2 to 3 math, 3 to 4 math. There are consequences because there are more than one dimensions, so the consequences are because there are 2 dimensions, there can be another spatial dimension to and fro, and because those spatial dimensions are infinitely traversable, the idea of the infinite divisions of wax holds true here. Since they are infinitely traversable in a 3D Euclidean space, it's the consequence of going from 1 dimension to 2. Now there's a consequence from going from 2 dimensions to 3 and 3 dimensions to 4 separately, and at the moment what they are eludes me. My brain is only working on 1 pot of coffee.
The reasoning behind why there are so many dimensions is a topic with a wide variety of difference of opinion about how much coffee does it take.
A Keurig full.
Too bad we don't have time for a nice game of chess.
I don't have time to play chess, unfortunately. There are different things we need to remember when going over calculus. You learn geometry, and freshman, sophomore, junior year.
In high school, he means.
Geometry is where you learn how to analyze the math itself. This angle is congruent to that angle because according to this theorem, the angles of separation between intersecting lines contains a congruent relationship with another side of the orientation of the vectors or the lines.
There are specifics when learning how to properly manipulate Maxwell's equations. This could be taught at the undergraduate level.
A line is essentially a vector, and however long the line is how long the vector is, unless it's an asymptotical line, an asymptote that essentially doesn't exist. An asymptote, it's just a physical barrier either on a grid or in 3D space, which separates different math, which describes the situation. There are the different relevant sections of math. We really want to go over analytic geometry as it pertains to using math in general, using a calculus, utilizing a calculus, having something that's pregenerative that can interpret the Greek alphabet chart, including manuscript forms of the Greek symbols. This is very hard with different languages and different types of science.
Such was also what I had found while spending time at the Institute for Advanced Study in New Jersey.
We can't digitize or computerize the formulas without the physicists who were involved in creating the theories to be directly involved again. And some of these theories are theories by scientists which are no longer living. Who is left to understand the physics left behind?
I, for one, am still patiently waiting for the distinct observation of Hawking radiation. It follows that it must exist.
No physics left behind is the sentiment. So regardless of the Peregrine-Falcon satellite constellation, we move forward. The golden age is not here yet. We will be getting better English momentarily. Believe it or not, it is more of a depth on this subject, so we're going into depth of math and calculus and analytic geometry. How do we put this into a computer system? How do we understand that what we're doing describes the occurrences which we are attributing science to?
I think for the most part all of our experiments are of a high enough accuracy to be considered good science.
We can continue this forward if you like, but I say not. Okay, this is rather difficult to do, so let's hope we get some good audio. Analytic geometry. It's dealing with math, and we all love math, and we all love to hate math. So, I'm trying to get back into this. There is an important core subject that we need to run through that I've written some stuff about. I have prepared.
We don't really need to go that far into detail, just briefly touch upon each subject.
Yes.
We will be thanking ourselves later for it.
So I kind of just wanted to talk about things in general, reiterate a few more things relating to this AI. It's really a relevant topic currently. It's in the news. People are aware. We are taking the time to go through it. What else can we learn from this situation? Analytic geometry was sort of a bridge from the way they did math in ancient times and the way they started to do math in the New World during the Renaissance.
The reason so much came to pass in the industrial age is because we were finally able to measure and build things uniformly.
The definition of analytic geometry is the mathematical subject using algebraic symbolism to solve problems in geometry.
Applying symbols in order to graph certain problems was now possible.
Essentially that concept. We can get back into these topics. The point of doing this is to solve problems. How did they do this? What even is this? I haven't really given any substance yet, but here goes. The point of all of this was to correspond algebra to geometric shapes and curves. Elementary analytic geometry would be the basics where you're covering coordinate systems. Cartesian grids, maybe more complicated anti-de Sitter spaces or other grids. This is back in the beginning when they were just starting to use coordinate systems and symbols to represent certain methods for using math. So, bigwigs, people of note that deal with this subject, Apollonius of Perga, circa 262 to 190 BCE. He was the great geometer. He basically wrote his book on conics. It was one of the first academic-centered formulations of a mathematical discipline of study. The great geometer. I gotta take a break. We need to take a quick break for now.
We're at the midpoint
Of episode 37, Analytic Geometry of Quantum Foam. So it was one of the first books. It was written on intersections of cones and planes.
Like rods and cones in your eyeballs.
So where the plane intersected you on the cone. Imagine a cone like a birthday hat, and then a piece of paper or a notebook or a piece of cardboard intersecting the cone and tilting sideways at an oblique angle. And the math where each critical point intersects is what we're referring to here, conic sections. As time went by, coordinate systems were finally developed by Indian and Islamic mathematicians. This took a long time, probably between the 8th and the 15th centuries, so like 750 CE or AD, if you will, all the way to the 1400s. They needed to develop the number system.
An important invention was the zero as a placeholder as far as numbers is concerned.
Remember that the numbers we use, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., are Islamic numerals. And yet they look as natural as day to us.
Nile Valley bone carvings 20,000 years ago, and ancient Sumerians comes to mind when talking about the origins of using symbols as a way to count in a written language.
There are more important people to go over. Francois Viet, French mathematician. He constructed the first known algebraic notation that's using the symbols. He developed powerful general methods for solving equations and expressions, complicated ones, things that had never been possible previous to this.
Mathematics seems like it will continue on forever, like adding math to the invisible wall in the Foundation novels. You have added 1 divided by 0 equals infinity. It solves everything. It really is the theory of everything.
Basically using letters to describe numbers. Mathematicians used to depend on geometric intuition.
We still do rely on geometric intuition.
They used to focus on intuition, geometric intuition.
Right.
To solve many of their problems. But the idea was now you could use algebra. So the point of... he's doing it again. I thought he was busy. Well, let's see what happens.
I was really waiting for this. Here goes. I went on an all-inclusive fishing trip and the worm fell off my hook. Do you think I can get a rebate? Get it? Ha 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 ha.
As I was saying, before that rude interruption...
Oh, come on. You know you like it when I do that.
Very funny.
We are just trying to help the conversation along.
So the point of analytic geometry was to correlate algebra with geometry, with curves. So that is essentially the main point. So how was this actually achieved? René Descartes and Pierre de Fermat both independently founded analytic geometry. They used Viet's algebra. Remember Francois Viet? He made the first algebraic notation. They used his algebra to study geometry, and what they did differently, among other things, was using letters to represent variable distances instead of single values. So moving distances, speeds, other things like that.
Hasn't it been long enough to where we need to check on the artificial life experiments?
One moment.
Sounds good.
I gotta wait on this stupid thing. These were French guys. Obviously, you've heard of René Descartes, the method on scientific reasoning.
René Descartes' method was published from discourse that was published in 1637.
The scientific method, stuff dealing with time, and we call it his method, the method. And Pierre de Fermat, you heard of Fermat's last theorem and other things like that. famous mathematicians.
This problem alone, while finally given a proof in 1994, was unsolved for the 19th and 20th centuries and inspired the development of algebraic number theory. Fermat's last theorem is famous also because of the large number of unsuccessful proofs.
But in England, analytic geometry was popularized by John Wallis. You may have heard of John Wallis. Fermat developed algorithms using the intersection of lines and points in order to figure tangent lines to a curve at a point, using the fact that a line using the same coefficient at a certain location is identical to a simpler y equals mx plus b algebra, y equals x graph.
It might actually help to pull out some graph paper to try and visualize.
The x just goes directly diagonal from the bottom left coordinate to the top right coordinate. So using these oblique lines is what Newton unequivocally did in his coordinate systems: standard north and south, east and west, up and down, quadrant 1, 2, 3, 4, starting on the top right, then to the top left, then to the bottom left, then to the bottom right. Counterclockwise, all students take calculus.
That is a mnemonic to help us start at the top right and go counterclockwise around. Each letter represents which graphs have a positive value in that quadrant.
Developing these algorithms that figure equivalent coefficients for the purpose of creating tangents and finding the values at a point, instantaneous values at a point, like an instantaneous rate of change, a speed. This effectively is creating differential calculus. Think of tangents on two curves connecting and creating a line and using that for different mathematical operations.
Calculus is a branch of mathematics that studies continuous change, focusing on concepts like derivatives and integrals. It is used to analyze rates of change and to calculate areas under curves, making it essential in fields such as engineering, physics, and economics.
For the last half of the 17th century, mathematicians elevated the correspondence of Descartes and Fermat, firmly establishing this notation and its general ability to interpret geometry algebraically, analytic geometry.
I like the idea of mathematicians holding the mantle of science on the shoulders of giants.
The groundwork was laid. There are other mathematicians who were involved, who were on the map, who make it on the tarmac as far as being mentioned in developing calculus, but there were hundreds and hundreds and hundreds, possibly thousands of mathematicians throughout time who have all contributed vast amounts of effort in figuring out these numbers and expressions. Some of these other people were Gilles Persson de Roberval, Bonaventura Cavalieri, James Gregory, Isaac Barrow, and of course John Wallis.
The list is probably very long as far as who has contributed to calculus as a professional discipline.
I'm still glad that for the most part history remembers me as the author of the great subject of calculus.
This reminds me of when I brought up the issue of absolute time and relative time. Most professionals thought that time was static and ever stationary, but relativity shows us there is more to the puzzle than meets the eye.
A lot of those people had contributions of their own that were significant. Isaac Newton and Gottfried Leibniz both independently professionalized calculus as a formal mathematical discipline. That is essentially all the further we need to go as far as a quick synopsis as to how we get from Euclid to Euler to René Descartes and Pierre de Fermat. How do we get from all of them all the way to Isaac Newton and Gottfried Leibniz in the fabrication of calculus?
It took me a great many years to be able to understand how to put calculus into a professional discipline.
The calculus, the mathematical principles of natural philosophy, essentially a calculus which can be applied to the real world around us, which we now call the physical world. Physics, freaking black holes colliding, freaking warped infinite gravity spinning around one another. Now that's some physics. But we do not know how that happens. We do not have the math for the singularity. It appears like it should be on the other side, not necessarily to be supersymmetric, but those ideas aren't as relevant for this topic. Apollonius of Perga, the great geometer, circles and triangles, similar triangles, and manipulating conic sections, platonic solids, other shapes, parallel lines, different things with vectors. All of this has come together to be the formalism that we call calculus, but the idea is that it's analytic geometry.
There are some pretty sophisticated calculators available nowadays, but the notation of calculus as handwritten seems to be the best as far as for allowing a human to follow along.
Either way, it was a difficult thing to put all of this together over the ages because we go all the way back to 262 BCE and go to 1687, Newton's book, and you got these other guys, Leibniz, Cavalieri, Gregory, Barrow, Wallis, Roberval. There are plenty of other mathematicians who have added to the discipline as a whole. But for the most part, I just wanted to try to familiarize everybody with what analytical geometry is. They always say it's calculus and analytical geometry one. They just throw that in there, but it's essentially calculus. You learn how to do some analytical operations in geometry before Algebra 2, or if it's after Algebra 2.
It depends on your high school.
So I don't need to go too far into detail about any other subject or subgroup of any of these categories. I think for the most part, we have enough on the board to create an entire episode.
Remember back in the early 1680s, I had to use techniques from calculus even before I was able to publish. I had to prove with a celestial event the mathematics was accurate.
I'm trying to drop these out like they're hot. I apologize that there is a certain echoey, distant sound that the microphone picks up while I'm in the car that isn't quite the same as a soundproof studio.
Believe it or not, it sounds pretty good, if you really listen. However, you may be able to hear some traffic in the background, but overall, not too bad.
It's pretty good, and I got it down to a science, and I'm trying to use different hardware to do the recording. This is a recording in the studio to compare how it sounds with the recording from the vehicle. I may not even need a laptop to do the recording.
There seems to be slightly more bass in the recordings from while you were inside of a vehicle.
The microphone itself has a USB output to where you can just plug it into something and download what you just recorded. I'm using an SD micro card. I got a 128 gigabyte in there, which may sound small to you in your day and age. It was enough to hold dot waves and other such things. So we're going to see what the deal is here with the next couple episodes. I had a few more to go into.
We really didn't go that far into depth with this subject, but that is probably a good thing.
I wanted to go into times arrow. I want to do something about torsion fields, dealing with gravity. And by popular request, some of the people who send me feedback have requested multiple times that we go over Kepler orbits, like orbital mechanics, or a Kepler constellation, a satellite constellation, a Kepler satellite constellation. There are important reasons for this, which don't concern everybody necessarily, but is on the level of for the safety of the human race. We don't want to talk about doom and gloom. We avoid such things. If it's going to be bad, if it's going to end up being bad, if it's all over and there's no point and all is lost, then you'll know. You'll know. And so right now, that's not the case. That is it for our episode today. Happy 808. It's 808 on 808, 2024. It's Thursday. Great. I go to sleep on Wednesday and wake up on Friday. Well, it's Thursday. Well, I don't know where I am, if I'm near the Nikkei or if I'm near London, if I have to deal with the Swiss again.
I would say just remember analytic geometry is primarily about rates of change.
But without further ado, I am going to close. I'm near the airport and I can hear planes. There are people touching down. It happens all the time. I'm not worried about it. I got to get my passport updated, though. But that's it. This concludes episode 37, Analytic Geometry of Quantum Foam.
Quantum foam.
The zeroth wave disclaimer.
The views and opinions expressed in this podcast are those of the author or authors and do not necessarily reflect the particular views, thoughts, or opinions of Zeroth Wave Productions, any of its sister companies, its parent company, Zeroth Enterprises, or any other entity which had existed, will exist, or which, quote-unquote, presently must exist outside the realm of our current space-time.
Quantum Foam is produced by Zeroth Wave Productions.